Marcus, Thomas, Julia, and Malcolm. They're all undergrads except for Malcolm, who is a graduate student in geophysics and is doing voluntary work with me in astronomy. And actually, his project is very cool. It's about clumpy galaxies in hydrodynamical simulations. And what he found was that TNG 50 doesn't produce clumpy galaxies, but what he found was that if you just increase the density threshold for star formation, then suddenly you get a whole bunch of clumps. So I can't talk about that talk today, but I did talk about that last week during the pre-workshop meetings. And so if you want to know more about that, please ask me. Today, I want to tell you about blue-centered galaxies in the cosmic web, which is work mostly done by Marcus, and you'll see a few cameos from plots by Thomas and Julia as well. Okay, oh, by the way, on their own initiative, they started their own Discord server, and they called it SWAG, the SFU Woo Astro Group. I promise you, I had nothing to do with that name, all right? But that's what they call themselves. I'm at Simon Fraser University. Okay, so the question that I am trying to ask is, why are there so many blue-centered galaxies? And there are a lot. This is a histogram here from the DESI Legacy Imaging Survey. This is Layout All 2021, and there's a histogram of color gradients, okay, in different bands for spectroscopically confirmed galaxies in the nearby universe. This here is the zero line. And to the right, they've defined their gradient, those are the blue-centered galaxies. That's a lot. That's like 40% or so by eye, depending on which band you're using. I'm taking this plot. I just screenshotted it from Aldo's talk, and this is showing the Stephenson et al. Paper. They plotted their red dots here as blue-centered galaxies. So you can see there's a ton of them, and they happen to be more lower mass. Other clues that we know about blue-centered galaxies is they tend to be small and dense. Now this here is a plot of the size-mass relation for the manga galaxies, and this is just star-forming isolated galaxies, and they've been color-coded by the gradient of star formation this time, not color. But the blue dots are the blue-centered galaxies, so anything below 0 here is blue-centered, meaning that the star formation is happening in the centers. And you can see that they tend to be lower down on the plot, so they are smaller. Blue-centered galaxies, this is a plot of sigma 1. This is the central density within 1 kiloparsec of the center. And this is stellar mass. And you can see that because stellar central density is tightly correlated with the size, as shown by Chen et al., for star-forming galaxies at least. You can see that just as they are smaller, they are also denser, the blue-centered galaxies. So the blue-centered galaxies here are smaller and denser for their stellar mass. Okay, so this we actually showed in 2019, but we didn't call them blue-centered. We called them some convoluted name like galaxies that have centrally concentrated star formation or something. But sorry? Yes, but blue-centered, we're sticking with blue-centered now. That's far easier to roll off the tongue. Okay, so blue-centered galaxies are small and smaller and dense. Okay, so we wanted to know where they come from. So one thing we wanted to study was a simulation. So we decided to test, first of all, in TNG 100 whether or not we see the same thing. And the answer is yes. We do see that blue-centered galaxies that are isolated and star-forming tend to be small and dense as well. Okay? So, there we go. Okay. Yeah, so they tend to be small and dense. Okay, so what's going on here? Why are there so many blue-centered galaxies? So one project that we're exploring right now, this is work in progress, is the contribution of mergers to blue-centeredness. And here's a project by Julia. She is looking at merger remnants in Sloan, and she is looking at their color gradient as a function of time since the merger, which was calculated by Sarah Ellison's group, but in a paper Ferreira et al. 2024, 2025. And this is work in progress, and what she found was that merger remnants start off as very blue-centered, then they become more red-centered later with time. So that makes a lot of sense. But I'm not going to dwell on this result for the moment. I do want to tell you a little bit more about how the cosmic web might be contributing to blue-centeredness in galaxies. So the idea is, in this paper in 2022, we measured the angular momentum of the accreting gas that is falling into a galaxy. And how we defined that was all the gas particles that are falling into a radius of half RVR so that they'll reach the galaxy within a reasonable amount of time. And all those gas particles, we computed their specific angular momentum. We also did the same thing for the disk gas. And what we found was that the angular momentum is correlated with size and density as you would expect. So here is what we found. This is now the same size mass plot and density versus mass plot, now color-coded with the SAM, the specific angular momentum of the accreting gas. Blue here is low angular momentum, so the impact factor is such that the gas is falling closer to the center of the galaxy. And what you see here is that in the same areas of the plot, the small galaxies and the dense galaxies, the specific angular momentum is low. So this makes a lot of sense, right? If the gas is falling closer to the center, you expect the gas to be forming stars near the center, you'll increase your central density, and you'll end up with a smaller galaxy if this is some scale radius like the half-mass radius or the half-light radius. So this makes a lot of sense. This is answering some questions, but the question that we wanted to further ask was, well, why do some galaxies accrete gas with low angular momentum, and why do they accrete gas with high angular momentum? So the idea that we wanted to test was perhaps the position in the cosmic web determines the angular momentum of the accreting gas, right? So the idea is that if you're in a high density environment, a thicker filament like this, you are more likely to have gas fall in with higher angular momentum. So some papers such as Legel et al. Have shown that big, dense, thick filaments are surrounded by these vortices because, their filaments are the intersection of sheets. The gas will be flowing in vortices. There's going to be a lot of chaotic flows of gas, and they'll end up in your galaxy with high angular momentum. So that was the idea. Whereas filaments, lower density filaments, galaxies that are living in thinner filaments are more likely to accrete gas with lower angular momentum. Now, the gas flows have not yet been studied in the thinner filaments because part of the reason is because thinner filaments are much harder to define and find. But this was the idea we wanted to test. However, there's one more factor that might also influence the angular momentum of the gas falling in, and that is the orientation of the galaxy. So it has been shown, at least in 2015, that if you have your accreting gas falling in at a different angle than the spin of your galaxy, you will find that your accreting gas will lose more angular momentum to get into your galaxy. And we did confirm that in TNG 50. So here, the x-axis is the accreting gas alignment. So if you measure the angular momentum vector of the gas falling in and the angular momentum vector of the galaxy itself, the angle between those vectors is the alignment, or the misalignment. So 1 means you're completely aligned, and -1 means you're completely anti-aligned. And the y-axis here is how much angular momentum you're losing. So that's just the difference between the angular momentum of the gas falling in and the angular momentum of the disk gas. And what you're finding is, what we found is that the more misaligned or anti-aligned your gas is in terms of the angular momentum vector. This is not the same as the geometric alignment with the filament that Farhan talked about. This is the vectors of angular momentum. If they're anti-aligned, you will find you will lose a lot more angular momentum. The gas will fall near the center of your galaxy, and let's see what happens when that happens, okay? So there are two effects, the alignment and the filament that we wanted to test. So here we have a plot of the filament density. This was directly from Farhan's slime mold cosmic web talk. So see his talk as well as his papers about how that's calculated. This y-axis is that alignment number. So 1 is aligned and negative is anti-aligned. Okay, so this is, those are the two axes. The contours show the distribution of points in the plot. Most galaxies are pretty much aligned. That makes sense because galaxies are being fed by gas accretion, so a lot of them are aligned. Now let's see what happens then if we color code this by the angular momentum of the gas. So here we have the angular momentum. This is the disk gas, but the accreting gas actually is the same. The angular momentum is lower if it's red. It's higher if it's white. And what you can see is that the gas angular momentum depends on both the filament density and the alignment of the galaxy to the accreting gas. So you get lower angular momentum for misaligned galaxies, and you get lower angular momentum in low density filaments. So both of those effects are important for determining the angular momentum of the gas in your disk at the end of the accretion. Okay, so we talked about angular momentum. Our original question was about the sizes, the densities, and the color gradients. So does lower SAM also correspond to blue-centered galaxies and smaller and denser galaxies? So, before I get there, you might complain that there's a mass dependence. There is a mass dependence. This is now color-coded by mass. There's a strong mass dependence. More massive galaxies live in denser filaments. So we took out that mass dependence and we computed a relative value of the angular momentum relative to its mass bin. Is it like over? Does it have an excess of SAM or an under, like a deficit of SAM? And it tells the same story, basically. You do get lower relative angular momentum in the thinner filaments, the low density filaments, and if you're misaligned, if your gas is misaligned. Okay, so let's see then. This was the same plot that I showed you before. That was the SAM. Now this is color-coded by the gradient of the specific star formation rate. So this is whether or not you're blue-centered or red-centered. Blue is blue-centered. So what we're finding is that, so we already know that thinner filaments with misaligned gas gives you lower angular momentum, and we also get relatively bluer centers in the same corner. So that's really good news. It's all very consistent. So we have lower relative SAM and bluer centers. What about our sizes? Well, we have this one on the left here is the color-coded by the half-mass radius. It's also a relative value relative to the mass. And we get smaller sizes in the same corner where the angular momentum is lower and where the galaxies are bluer centered. And we also have denser cores. This plot is color-coded by the sigma 2. This is the central density within 2 kiloparsecs. So we get denser cores, smaller sizes, bluer centers, and lower angular momentum all in that same corner of the plot. Okay? So smaller and denser galaxies if the accretion is misaligned, and you have smaller and denser galaxies in low density filaments. So this is work in progress, and these results, the previous results I showed, have been submitted, and these are a new avenue of exploration that Marcus has been doing, which is to look at black hole activity. And what we see here, this is now color-coded by the relative black hole mass. It turns out, so black hole mass relative to the stellar mass, you can think of that as black hole mass divided by stellar mass. But what we get is relatively bigger black holes in the same corner where the angular momentum was lower. He also plotted this by the amount of kinetic feedback, the energy in kinetic feedback divided by as a ratio of the thermal feedback. So if you remember in TNG, those of you who aren't familiar, in TNG, what is it that quenches galaxies? It's kinetic feedback from the black holes. So the amount of energy here, he's color-coded it such that blue is higher. So he's got more quenching energy in that same corner. So this is there's a lot of avenues to explore in terms of the cosmic web and how the cosmic web influences galaxy evolution. This is preliminary work, by the way, so this could change. Okay, what else? Okay, so we also wanted to see whether or not this is the same thing in observations. Okay, good. All right, so we cannot measure, unfortunately, gas alignment. The y-axis we collapsed. But the filament density was also from the slime mold cosmic web measurements on the Sloan catalog itself. And so we decided to take a look whether or not we see the same relations. And the answer is we see the exact opposite relations from what we saw in TNG. So for example, here we have the half mass radius as a function of filament density. The points are the average radius in those bins of filament density, and we find the opposite relation. Galaxies in denser environments, denser filaments, tend to be smaller for their mass. This is a mass bin. This is core density. Also, we have denser galaxies in denser filaments, which is the opposite of what we found in the simulations. And lastly, the color gradient. This is not SSFR gradient. This is now color gradient because there were very few galaxies that we could do this with. But the color gradient, red centered, is at the top, and you can see that they're more bluer centered in denser filaments. So this is quite a puzzle that we are thinking through right now, and we welcome comments and feedback from the audience. But basically, this is also preliminary work that we're working on with Thomas. So in summary, small and dense galaxies are bluer centered and accrete gas with lower specific angular momentum. So that's your size mass plane, color coded by color gradient, and the blue centered galaxies here are smaller in size. And they are also denser in sigma 1. And we see the same thing in TNG, but when we color code this by specific angular momentum, we find that the area in the plot where you have blue centered galaxies also corresponds to the area in the plot where you have lower specific angular momentum of your accreting gas. The galaxy properties also correlate with both the filament density and the alignment of the accreting gas. So in the sense that a misalignment of accretion, so if you're lower on this plot, it results in lower angular momentum and smaller galaxies in denser and bluer centers. So that's, but over here, if you are in denser filaments with aligned accretion, you have rent-centered galaxies. You have high specific angular momentum, larger size, diffuse cores, and smaller black holes as well. So that's the preliminary result. Down here in that corner, thinner filaments or low-density filaments, misaligned accretion, you get blue-centered galaxies, lower specific angular momentum of your accreting gas, smaller sizes, denser cores, and bigger black holes. And this was the picture that we had tested with the filament density, but alignment also matters. All right, so but the galaxy properties in the Sloan Digital Sky Survey have the opposite trends. Galaxies are smaller, denser, and bluer centered in the denser filaments, which is an exciting puzzle to try to solve. All right, thank you. I'll take questions.
Thanks, Joanna. This is really nice. So related to a conversation that Sandy and I were having yesterday, are these properties specific to the gas in the filaments, or if you had tried to measure, for example, the angular momentum alignment or filament density in a pure dark matter simulation, have you tried that, and do you think that you would be able to see discriminating features in the dark matter, or is this purely something that's happening in the gas?
That is a great question. Now, we haven't looked at the dark matter because we were originally asking the question, why are blue-centered galaxies, right, why are there so many? Yeah, and so for that we would need gas. So we didn't look at that, but I can imagine that the kinematic properties of the halo may also affect the gas as well. So right, that would be a good thing to check.
Of course, with TNG, you have the dark matter only runs, yes, so you could try to match, yes, between the full. Yeah, that'd, yes, be very cool. Thank you.
Yeah.
If you just pass the mic forward, and then we'll do Frank.
So could you please get back to the Sloan slide? So you construct the filament catalog also using MCPM method, right?
That's right, yes.
So is the tracer density, or say galaxy density, in this Sloan service comparable to those in TNG and TNG 100?
So that is a good question. I don't actually know the answer to that. Farhan, do you know the answer? Okay. So these are relative values.
Okay.
But that is a good question. If they're not the same, then we're either missing a lot
Right.
of density or there's something else wrong.
That's what I care about.
Right.
Okay, so just Barry starts coming up while we have another question. Yep.
Great stuff. You talked about the magnitude of the angular momentum accreted, low versus high, and the alignment.
That's right.
There's a third property that could be important, and it's the coherence of the angular momentum.
Okay.
You can have all the gas come in with zero angular momentum, or 50% come in with positive and 50% with negative. So have you looked at that, at the coherence of the angular momentum and how that correlates with properties?
That is a good question. We have not looked at that, but we figured that if some was negative, some was positive, that the net effect would be more important, but we didn't check coherence. It might actually be important as well.
Okay, let's thank Joanna again.